Last week, especially in the exercises, there was something that I strongly hinted at in the hope that you would discover it for yourselves. That is that writing proofs and writing programs are extremely similar to each other. At least they're extremely similar if the language designer carefully arranges things to make it obvious, which we have done. The technical name for this idea is the Curry-Howard correspondence, but you don't need to know that. It's basically a long list of analogies that various concepts in programming and in logic look very similar to each other. So let's start with pairs. So we define pairs like this: pair, data pair AB equals make pair AB, and we can name the fields first and second. Now, a pair AB is a thing that consists of an A and a B, and it behaves a lot like the formula A and B. So let's look at a proof involving A and B. For example, I can say prove A and B, prove A and B implies B and A. Let's quickly write this proof. I say by imp I. Now I'm given A and B, so I say from A and B in order to split it up into given A and given B. And then I say by and introduction to reassemble those givens back into a proof of B and A. Okay, now let's look at the program swap, which is a function from pair AB to pair BA. So its type signature looks like this. Okay, so notice that the type signature here looks like the formula here, and the program we're going to write looks like, or is going to look like, the proof. So let's say define swap X, and so X is a pair, so we're going to write from X to decompose it. So that splits it up into the first field and the second field, and then I'm going to reassemble them by calling the constructor make pair and say second with parameters second and first. So this is the swap program. Okay, so let's look at both of these and squint a bit. So clearly they're not exactly the same. We had the choice as language designers to make them look more like each other, but we thought that would have been confusing. So they're not identical, but they do have the same structure. So having the input X is like having given A and B, and then writing from X to inspect this input is like writing from A and B. And then having it in this form, where we have the first and the second field, is like having given A and given B. And then calling the make pair constructor is like saying by and I. Okay, let's do another example. So here's the definition of a tagged union type. I can write data either AB equals left A or right B. So whereas pair behaves exactly like the and connective, either behaves exactly like the or connective. So here's a formula we can prove. A or B and C implies A and C or B and C. So let's quickly prove this by imp I. Then I have an and formula, so I do from it so I get given A and B and given C. And then, so I'm given A or B, so now I do a from on that in order to do a case split into the case where A is true or the case where B is true. So now in this branch I have A, so I'm going to prove this thing by proving the left thing by or introduction left. Now I have to prove A and C, so I'm going to say by and I. And then on this branch I say by or introduction right, where now I say prove B and C by and I. Okay, now we can write a program with the corresponding type, which is pair either AB C to either pair AC, pair BC. So those of you who are on the ball might notice that the proof version of this was in the week 2 exercises and the program version of this is in the week 3 exercises. So I went as far as I possibly could of allowing you to discover this similarity for yourself. So back in the exercises, I called this thing thing. So let's say define thing X from X. So X is a pair. So we split it into a first field and a second field. And then the first field is an either. So we say from first to case split on whether it's a left or a right. And then in this case, we can build the output by saying left of make pair x second. And here I can say right of make pair x second. This is spoilers for those of you who are watching this before you've done the week 3 exercises. Okay, so again, these look like each other. So this from A or B is like saying from first, and then you case split of whether it looks like a left or whether it looks like a right. And then this, where we build this output from the constructor left and make pair, this is like or introduction left and I. And in the other branch, it's like or introduction right and I. Okay, so in summary, the formulas that you can prove are in correspondence with the types for which you can write a program that has that type. Actually, there is a bit of a lie in the last sentence I said, which I'll come back to. But proving and programming are not exactly the same thing. So one important difference is that in logic, we normally only care that a formula is true. So once we've found one proof of it, we usually don't care about finding another proof. But in programming, we really do want to distinguish between different programs that have the same type because they do different things. That is to say, we run programs, we don't run proofs. So here's an example of that. I can say prove A and A implies A. So this says that if something is true twice, then it's true once. So I can do this by writing by imp I. And then I have given A and A, so I can say from A and A. And actually ask accepts that, but I can fill in the missing line of given A, prove A given. So in ask, once something is given, if it becomes given again, ask just ignores it. So I could actually say given A comma A, but that actually makes no difference. Whereas in programming, there are two different programs of this type, one which returns the first thing in the pair and one which returns the second thing in the pair. And these are different. So I can say define fx from x, and it gives me a first field and a second field. And now I really have to make a choice. So I can say equals first, and now this is the program that returns the first of the pair. Okay. So I'll quickly say something about the other connectives. The connective true turns out to correspond to the singleton type that you wrote for the week 3 exercises, which is data unit equals unit. False is very interesting because false corresponds to a type that has no values. So it turns out that in ask, you can write data nothing equals and stop. And ask will accept this as a valid definition of the type with no values. Okay, so in ask, we can prove that false implies anything. We can prove false implies A by imp I, and actually ask will accept that as a complete proof, but I can say where given false, prove A from false. So the from false rule encodes the fact that false implies everything. So similarly, I can write a program called magic that will turn a nothing into an A. So this says magic will give you a value of any type as long as you give it a value of type nothing. And how can I define this? Well, I can say define magic beans from beans. And if I send that to ask, when I say from beans, it is doing a case split on the different values that beans could take. Beans is a value of type nothing. So it looks at the constructors for nothing, discovers that it doesn't have any, and then accepts this as a complete and valid program. This definition, of course, is a Connorism. Connor is very good at naming things. So this is probably the most Zen-like function you will ever see in your life. This is a function that promises correctly to do something impossible, provided that whoever calls the function holds up their end of the bargain by providing a value of the empty type. So you could ask the question, what does this function do at runtime? And the only reasonable response to it is to unask the question because there is no runtime for this function. Okay, I should say something about not. So not behaves like functions into nothing. So instead of not A, we can write A arrows nothing. So for example, we can prove that if A, then not A. We did this in week 2 as an exercise. I can similarly write a function which will turn A's into the equivalent thing to not A. And this is actually very easy to define because one input is a thing and the other input is a function from things to nothing. And I can get a nothing just by applying that function to that input. Okay, so actually this is an example of functional programming in Ask. This function has taken another function as input. This is a thing that Ask can do that we haven't really told you about yet. Okay, so here comes the catch. We can also prove that not A implies A. This is a proof that we can write, and we have to use by contradiction. We have to use the contradiction rule in order to prove this. There is no program like this. Nothing implies A. It turns out it is not possible in Ask to write a program that satisfies this type. So this question mark cannot be successfully filled in. So there is nothing in programming which corresponds to the by contradiction rule in logic. So when I said earlier that writing proofs is like writing programs, the correct statement of it is that the things that you can prove, the formulas that you can prove without using the by contradiction rule correspond to the programs that you can write with a type. Okay, so now you've watched this video, I'm going to reveal that this was a sort of bonus video. This video is more like a sort of bonus 4th exploration for week 3. So in the next video, I'm going to get to the main part of the content for week 4, which is writing proofs about programs.